Hello everyone. In this chapter we will look at reactions of carboxylic acids and carboxylic acid derivatives. So this group is group 3 where we have a carbonyl group, and one category of group 3 is you have a carbonyl group and it's attached to another element. Let's call it as Z. There is going to be an atom more electronegative than carbon. It could be a chlorine, like a chloride, or it could be a hydroxy group, or it could be amine group. So the Z is going to be more electronegative than the carbon. That's one family. And then the other family under this group is you can have hydrogen or alkyl group. And we know if it is a hydrogen, that's an aldehyde. If it is a alkyl group, that's going to be a ketone. Okay, those are the two groups in group 3. And here's a carbonyl group. We are familiar with this one. And the acyl group means a carbonyl group attached to an alkyl group, or a carbonyl group attached to an aryl group. Aryl group is the phenyl ring. Okay, any phenyl groups, and we call it both of these as acyl groups. There are two classes of carbonyl compounds, and this slide shows you one class where these carbonyl compounds with groups that can be replaced by a nucleophile. So the carbonyl group. So this is the acyl group, this part, and this is carboxylic acid, you have alcohol group. In ester you have a alkoxy group. Acyl chloride you have a halogen. And this is a amide, and this is a primary amine. So this is amide, a secondary amine in amide, and tertiary amine in an amide. These carbonyl compounds have a group that can be substituted by another group. And then the other class is going to be your aldehydes and ketones, carbonyl compounds with groups that cannot be replaced by a nucleophile. They will not undergo nucleophilic substitution. Instead, they will undergo addition. These carbonyl compounds do not have a group that can be substituted by another group. And that is because of the pKa values of the conjugate acids of the leaving groups of various carbonyl compounds. Okay, so now you can see that the acyl group is this group, right? So the acyl group, this has a halogen, this has a alkoxy group, this has a OH, and this has a amine group. And these are the leaving groups: chloride, alkoxide, hydroxide, amide groups. Okay, and they are carboxylic conjugate acid of the leaving group. Here is the hydrochloric acid. Here's an alcohol, water, and ammonia. Now if you look at the pKa's of these conjugate acids of the leaving groups, pKa of hydrochloric acid is -7. And alcohol about 15 to 16, water 15.7, ammonia 36. Now, if you look at the aldehydes and ketones, if you lose hydrogen, H as H minus, this is the base, and the conjugate acid hydrogen has a pKa is about 35. And then alkyl group, R minus, is going to be pKa is greater than 60. Now if you look at this, so this is a stronger acid, strong acids, and then as the pKa increases, they become strong bases. Okay, so you can see that the acyl groups of carboxylic acids and carboxylic acid derivatives, they are attached to weaker bases than the acyl groups of aldehydes and ketones. Remember, the lower the pKa, the stronger the acid. So these are lower pKa's. Lower the pKa, the stronger the acid. And then the weaker its conjugate base. So since the acids, conjugate acids, are stronger, these are becoming more weaker. Since they are weaker, it's easy to replace them with another strong base or a nucleophile. Okay. And what about the aldehydes and the ketone? The hydrogen of an aldehyde and the alkyl group of a ketone are too basic to be replaced by another group. You see how basic they are? So this is about 35 pKa, this is about 60. So they are very strong bases, and if you recall, like the sodium borohydride reduction of aldehydes and ketones, we created hydride, a base, a strong base. So removing a strong base by breaking carbon-hydrogen bond is very difficult. Similarly, remember we talk about the cuprates. Cuprates and Grignard reagent, we created alkyl nucleophiles and they were strong bases. So these are weak. Okay, so because of that, it's not possible to remove a hydrogen or alkyl group from aldehyde or a ketone. Okay. But in this section, we're going to discuss the reactions of carboxylic acids and the carboxylic acid derivatives. And they will mostly undergo substitution reactions because they have an acyl group attached to a group that can be replaced by a nucleophile. So this is a carboxyl group. Carboxyl group, see, you can represent, so this is how you write it, and then you can represent as a COOH or CO2H. And let's learn how to name the carboxylic acids. So we always give number 1 to the carbonyl carbon of the carboxylic acid. And let's look at some of these carboxylic acids. So the systematic name, so this has only one carbon. Remember, if you have a one carbon, that's going to be in alkane, methane, ethane, propane, butane, pentane, hexane, heptane, and octane, nonane, decane. So this is coming from methane CH4. Since it has a meth, we call it as a methanoic acid. And the common name is formic acid. 2 carbons coming from ethane, ethanoic acid. It ends in oic acid. Ethanoic acid, acetic acid is the common name. And this has 1, 2, 3 carbons, propanoic acid. Propanoic acid. And then when you have 1, 2, 3, 4 carbons, butanoic acid. Remember, when we are naming, we also include the carbon that carrying the carboxylic functional group, butanoic acid. So when there are 5 carbons, pentanoic, 6 carbon, hexanoic. Okay, and then this one has 1, 2, 3. 3 carbons is propane. If you don't have a double bond, there would be propanoic acid. Since there is a double bond, we can call it as a propenoic acid. Propene, so this is propene-oic, propenoic acid. Okay, and it doesn't have to say where the double bond is because there is no other place that you can put the double bond other than here. So propenoic acid or acrylic acid. And again, like I said, we give the number 1 to the carbonyl group of the carboxylic acid. With including that, we're going to number the longest chain. That would be this one would be 6 carbons long, hexanoic acid. Okay, systematic nomenclature, the carbonyl carbon is carbon 1. In common nomenclature, the carbon next to the carbonyl is the alpha carbon. Now, so this is the carbonyl carbon. When you are naming it systematically, you have to give the number 1 priority to that one to name the carbon chain. And then when we are looking at which one is the alpha carbon always going to be the carbon next to the carbonyl group. Okay, like this: alpha, beta, gamma, delta, epsilon, and so on. So this is the Greek alphabet. Okay. Okay, so in this molecule, 1, 2, 3, 4 carbons long, so it has to be a butanoic acid. So in the 1, 2, the second carbon, you have a methoxy group. So 2-methoxybutanoic acid, or this is also called alpha-methoxybutyric acid. That's the common name. And this one, 1, 2, 3. On the third position, we have a bromine, bromo. 3, 4, 5, pentanoic. So 3 bromopentanoic acid. And this one, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6 carbon long. So 4 chlorohexanoic acid or alpha, beta, gamma. Gamma chlorocaproic acid is the common name. So if a carboxylic acid has a ring, so this is going to be cyclohexane carboxylic acid. And this one, benzene carboxylic acid, or commonly known as benzoic acid. And this is how we're going to name acyl halides, acyl chloride and acyl bromides. So this one, if you have a halide here, we're going to name this part. It has 1, 2, 2 carbons, 1 and 2. 2 carbons long is ethane. So we call this as ethanoyl, ethanoyl chloride. Or acetyl chloride is a common name, ethanoyl chloride. You see this one also ends in oil. But we first need to know what oil is that. This is 1, 2, 3. On the third position we have a methyl group. 4, 5. So 3 methyl, 5 carbons long, pentane. If it is an acid, it would be pentanoic. But since it's a acyl halide, pentanoyl. 3 methyl pentanoyl bromide. Okay. Or beta methyl valeryl bromide. Lots of unusual names for the common name. Don't worry about it. And this one, excuse me, it has a cyclopentane ring, cyclopentane carbonyl chloride. Cyclopentane, and this is named as a carbonyl chloride. And how to name esters. Now the ester functional group, we have a carbonyl group and you have a alkoxy group, carboxyl oxygen. This is carbonyl oxygen. This is carboxyl oxygen. Okay. Now how do we name ester? First you will say the alkyl group on the carboxyl oxygen. So this is carboxyl oxygen, this part. Alkyl group on the oxygen, you're going to name that one first. CH2CH3, ethane, ethyl. So that is ethyl. And then this has, and this, and then you're going to number from here to find out the main carbon chain. 1, 2, 2 carbons long. So that is ethane. And it's going to end as O8. Ethyl ethanoate. Coming from ethane group, 2 carbons, ethyl ethanoate or ethyl acetate. And this molecule over here, our alkyl group on the oxygen, carboxyl oxygen, is a phenyl group. So phenyl, 1, 2, 3 carbons long, propane, propanoate. Phenyl propanoate is a systematic name. Phenyl propanoate or phenyl propionate. And for this one, again you first name the alkyl group on the carboxyl oxygen. This is methyl. And from this side we have 1, 2, 3, 4. 3 bromo butanoate. Methyl 3 bromo butanoate. Butanoate because 1, 2, 3, 4 carbons. Methyl 3 bromo butanoate. Okay. And for this one, again you first write down the alkyl group on the carboxyl oxygen. It's ethyl. Ethyl, and this is a cyclohexane ring. Ethyl cyclohexane carboxylate. Okay, that's how you name that part. The substituent attached to the O is stated first, and then delete the ic acid and add 8. Since this is an ester, if it is just a carboxylic acid, you would say oic acid, but since it's an ester, you're going to end it in 8. Now carboxylate ion salts. So carboxylic acid is an acid functional group when the hydrogen is lost, you're going to be making a carboxylate salt. So this is sodium 1 carbon methanoate, sodium methanoate, potassium 2 carbons ethanoate, and sodium benzene carboxylate, but this is a very common name. We say it as sodium benzoate, but the systematic name is sodium benzene carboxylate. And this is acetate, and these are common names: acetate, pyruvate, lactate. Naming amides. Amides so this is the amide part, CONH2. This has 1,2 carbons, so ethanamide, amide, 1,2 carbons, ethanamide, and this one has 1, 2, 3, 4 carbons. And on the fourth carbon has a chloro group in it. So 4-chlorobutanamide. So it's going to end in amide, AMIDE, since 4 carbons long, butanamide, 4-chlorobutanamide. And then this one going to be, it has a benzene ring, and then the carboxy group, benzene carboxymide or benzamide is this molecule. And then this one, in the previous ones, we had on nitrogen only 2 hydrogens of the amide group. Now here you can see one is hydrogen on the nitrogen, the other one is a cyclohexyl group. So then we have to indicate this also. How are we going to represent this one? So on the nitrogen we have a cyclohexyl group. So you have to say N cyclohexyl, and then from this side you have 1, 2, 3 propane, propanamide, N cyclohexyl propanamide. And then this one, on the nitrogen you have 2 groups. You have a methyl and an ethyl, and then the methyl and ethyl will be named according to the alphabetical order. That would be N-ethyl, N-methyl. So you have to say N 2 times, 2 different groups. Okay, even if it is the same group, you still have to specify like in the next one. So this is N-ethyl, N-methyl, and 1, 2, 3, 4, 5. Pentane should end in pentanamide, amide group. N-ethyl, N-methyl, pentanamide. And then on this one, you have 2 ethyl groups on N. So remember, you have to say N-ethyl, N-methyl. So likewise, here you have to say N-ethyl, N-ethyl. So we're going to combine those two, since both of them are ethyl-ethyl, N-N diethyl butanamide. Butanamide because you have 1, 2, 3, 4 carbons. N-N diethyl butanamide. Substituent attached to the nitrogen is stated first in naming amides. This is the structure of the carbonyl group, carbonyl compound. Now you know carbonyl compound is a very important compound or structure of organic chemistry. Lots of reactions are happening in carbonyl group, right? And you can see it is sp2 hybridization, 1, 2, 3 electron groups, sp2 hybridization, and it is a trigonal planar molecule, electronic and molecular geometry. Bond angle is about 120. Okay, and between these two going to be less than 120, since the pi bond, more electron denser, will make more space here. But don't worry about that. We can consider all of these as 120. Okay. The orbitals used in carbonyl group formation. So you can see there is 1 sigma bond and 1 pi bond. Okay, and your sigma bond, 1 sigma and 1 pi bond between the carbon oxygen. And then the other groups, if you have a hydrogen or another methyl group, they are going to be all sigma bonds. And you also have 2 lone pairs. And then the pi bond would be above and below, perpendicular to the sigma bond. Okay. So the sigma bond is being formed between the sp2 overlap, whereas the pi bond is being formed between the p orbital overlap, unhybridized p orbital. And your lone pairs also will be end up on sp2 hybrid orbitals on oxygen. So these carboxylic acid derivatives, like this is an ester, carboxylic acid, amide group, they are all have at least 2 resonance contributors. Esters, carboxylic acids, amides have 2 resonance contributors, and these are their resonance structures. So the oxygen lone pair of the alkoxy group can contribute resonance, forming a bond between carbon and oxygen, a pi bond, and then the carbon-oxygen pi bond breaks and gives its 2 electrons to the oxygen. So as a result, oxygen will be negative charge, formal charge oxygen, negative, having 1 bond, and this oxygen having 3 bonds have formal charge plus. Okay, and between these 2 resonance structures, which one do you think contributes the most? It would be this one. Okay, but this is also possible, and this is a resonance for the carboxylic acid, similar to ester. Oxygen lone pair forms a pi bond between carbon and oxygen, so you can see the nice flow of electrons. Atoms doesn't change its position, no atoms doesn't move, it's only the lone pairs and the pi bond moves, not even the sigma bond does not break. Okay, same thing for the amide. Nitrogen has a lone pair, so this resonance can be done, like I said, with the lone pairs and the pi bonds, okay, adjacent atoms. So you can see the resonance with the amide also. And the physical properties of these compounds, relative boiling points. Amide has a higher boiling point compared to carboxylic acid, which has a higher boiling point compared to ester. Acyl chloride, ketone, aldehydes, they are about the same. And these are some of the actual boiling points of these molecules. Now, why carboxylic acids and amides have relatively high boiling points? So this is a carboxylic acid. So you can see between 2 carboxylic acid, you can have intermolecular hydrogen bonds. So the hydrogen bonds are being formed between a hydrogen and any other small, highly electron dense atoms like nitrogen, oxygen, fluorine. Only nitrogen, oxygen, fluorine, when they attach to hydrogen, can form hydrogen bonds. You can have hydrogen on this alkyl group like CH3, but they cannot form hydrogen bonds because the hydrogen attached to carbon. Hydrogen needs to attach to oxygen, fluorine, or nitrogen in order to form hydrogen bonds. So the oxygen lone pair of 1 carbonyl oxygen can form a hydrogen bond with the hydrogen of alcohol group over here. Similarly, this oxygen can form hydrogen bond with this hydrogen. Okay. So this is why carboxylic acid have a higher boiling point, and this one is a amide group. So the amide group, you can have this resonance structure. Okay, and then also it can have dipole-dipole interactions. Oxygen is negatively charged, nitrogen is positively charged, so dipole-dipole interactions are possible between polar molecules. Okay, so as a result, amides and carboxylic acids have higher boiling point. Carbonyl carbon is an electrophile. Electrophile means electron deficient, right? So you can see that between carbon and oxygen, oxygen is more electronegative, carbon is more electropositive. The polarity of the carbonyl group causes the carbonyl carbon to be an electrophile. We have seen it before also. Nucleophiles attack to this carbonyl carbon. A nucleophilic acyl substitution reaction where, so this is the carbonyl group and you have another group attached to carbonyl group. This is sp2. So the nucleophile adds to the carbonyl carbon and then carbon oxygen bond pi bond breaks, and you are making a tetrahedral intermediate. sp2 carbon now become sp3 carbon. Then what happens is, now the carbon oxygen pi bond is going to reform. So the Y will be lost, and then this is the substitution reaction. So in the place of Y, now we have Z, carbonyl group reformed. Generally, a compound with an sp3 carbon like this bonded to an oxygen and another electronegative atom is unstable. So that's why this elimination takes place and regenerate the carbonyl group. If the incoming nucleophile Z is a weaker base than the base in the reactant Y, what happens if this one is weaker than the Y? Meaning carbon Y bond is stronger compared to carbon Z bond. So then the weaker base is eliminated from the tetrahedral intermediate. So this will add on to the carbonyl carbon and form the tetrahedral intermediate. But between the Y and Z, so this is more weaker. If this is the more weaker one, then it will eliminate the Z and we will get back the starting material. Z is weaker base than Y minus, so Z is eliminated and the reactants are reformed. If the incoming nucleophile Z is a weaker base than the base in the reactant Y, the reactants will be reformed. If the incoming nucleophile is a stronger base than the base in the reactant Y, what's going to happen? Again, Z will add on to the carbonyl carbon, form the tetrahedral intermediate, but the Y is weaker compared to Z, so then the Y will eliminate and we will get the substituted product. If the incoming nucleophile C is a stronger base than the base in the reactant Y, a new product will be formed. What happens if you have both groups about the same basicities? Z will add and you will form the tetrahedral intermediate, and there is a possibility that the mixture of the two products will be formed. You can get some of the reactants and also some of the products. So when a nucleophile attacks a carbon, the weakest bond breaks. For example, when a nucleophile like Z attacks an alkyl halide, the sigma bond between carbon and Y, if this is weak, that's going to break. And then we will get the SN2 reaction substituted product. When a nucleophile attacks a carbonyl compound, always it's the pi bond that breaks, not the carbon Y bond. It's the pi bond. The nucleophile adds to the carbonyl carbon and then it forms a tetrahedral intermediate, then they reform the pi bond and then the weaker bond leaves. Okay. So this is the relative reactivities depending on the basicity of the substituent attached to the leaving group. The weakest base is the chloride. Remember, the strongest acid is the conjugate acid of this base. HCl has a strong acid and pK is -7. And then the next basicity is the alkoxide ion. And alcohol is the conjugate acid which has a pK about 15 to 17. And then the water or hydroxide, and then conjugate acid is water. pKa is, again, we looked at it, about the same as alcohol. And then the strongest base is going to be NH2 minus. So the relative basicities, chloride would be easy to lose, then the alkoxide, alcohol, and then it's going to be NH2 would be the strongest base, which is harder to lose. So if you put these in our carboxylic acid derivatives, these are the compounds. Acyl chloride would be most reactive, then the ester, then the carboxylic acid, and then the amide. Okay. We'll stop here and then we'll start again in the next session.